All right, next up we have Andrew Ash and Josh Anderson. And they're going to be solving RNA structures through computation.
Okay, yes, so as we were introduced there, my name is Andrew Ash, and we're working on RNA secondary structure prediction.
I'm Josh Anderson. We're working with Dr. Heitch, Dr. Bader, and Dr. Harvey, who represent math, computer science, and biology here at Georgia Tech, respectively. So this is a highly cross-disciplinary project. So as you probably remember from high school, there are 4 bases in DNA, your A's, T's, C's, and G's. In RNA, you actually replace the U with the T. And the A's and T's pair and C's and G's pair make that nice double helix you see in DNA. However, RNA is single-stranded when it comes out of the cytoplasm, and it doesn't always form nicely. It likes to fold in on itself because that's a lower energy, that's a more stable structure. So as you can see, the bases pair like this. Once again, T's replaced with U in RNA, but pair similarly. And so what we want to do is we want to find how it folds in on itself after it goes out of the cytoplasm. And so we use different computational techniques to try to achieve this.
So what do we start with? A huge list of A's, T's, G's, and C's. This is what the RNA strand looks like, and we need to try to predict from here how it's going to fold in on itself. So this is called the primary structure, which means it's just one long strand of A's, T's, G's, C's, and U's. But it's going to fold in on itself a little bit later, and we're going to try to predict what that looks like.
This is the secondary structure, which is what we are currently trying to predict. As you can see, it's essentially it can be broken down into a list of things that pair with one another. If you know what base pair I pairs with, then you're done. So for all I. So what we have here is that structure.
So after that is the tertiary structure. So looking here, the first one was only in a plane, what pairs with what. But it turns out that 3D space doesn't work in a plane. It folds in on itself in a very, very complicated way. So this right here is the sort of thing that you could expect to get on the tertiary structure. And at this point, no one's trying to predict this because this is way too hard. Let's stick with the secondary structure.
So these are the different possible substructures you can obtain in an RNA folding. And what we try to do is we just try to find the best for each particular case, the lowest energy. If this subsection will form a hairpin or a bulge or whatever, and if we find all the smallest subsections, we try to put them together and hopefully find the smallest total structure.
So lowest energy. Every state, every physical thing has a state. It has an energy when it's at the top of the hill, the energy at the bottom of the hill. Where do things go? To the place with the lowest energy. So just like a trike going down a hill, it turns out that RNA strands will fold into the ways that give them the lowest energy. And this is what we call the minimum free energy format. So the way that we calculate this is we need to look at every single possible folding, and we can score it. And the one that has the lowest energy score is the one that we're going to look at. Well, that's a whole lot of different formattings of foldings. And so we can use a technique called dynamic programming, which is basically the idea that once you calculate something, store it, and you can come back and look at it again later.
And God willing, when we're done, we'll have a predicted structure. And as you can see, here's a structure predicted by someone else's program. And it's, as you can see, the different kinds of structures are labeled. There's a hairpin, a multi-loop, and an internal loop, and these are all the smallest possible for that particular part, and thus add together and make the smallest for the total structure.
So we have our predicted folding, and we can measure through science the way that it actually folds. So when we compare these two together, we need some sort of idea of how well we're doing. And that's what this picture here shows. The red structure there is the pairings that we predicted. The green is the way that it actually works in the real world. Black is the overlap. So you can see we're doing relatively decently, but could be doing a lot better.
This fierce-looking bearded man behind us is that's Boltzmann. That's Luke Boltzmann. So we use one of his expressions to help find the probabilistic distribution of possible foldings. So the probability of the folding is proportional to that, where G is the energy and everything else is a constant. And so we just sum up G over all possible structures to get our what's called the partition function. And we do that by fixing a small substructure, as we see here, and then say that stuff happens on the right, stuff happens on the left, and that's independent, so you can just multiply them together, which is very convenient. So all we have to do is find a small substructure and then trust the dynamic programming.
So here's what we can do now. We can count all of the structures that have a particular folding, and we can take the probability of that out of all of the structures total possible for the folding. Using this, we can use our fuzzy D20s, and we can predict right here the probability of any particular pairing in this RNA strand. So we can score this and see that down there, not very likely, up at the top, relatively likely. So we also work with the mathematicians. And what mathematicians do when they have their breaks is they go on conferences out to tropical locations and they come together and bang their heads together to get some very, very complicated math results. So we're going to turn out and look here in a second the kinds of things that we get as a result of these conferences.
And of course they call it tropical geometry, in which they take the main function, which we normally use as addition, and have it be minimization, and their product is an addition. So this is actually very close to what we've been doing because in the MFE we use minimization and addition, but instead of minimizing all the loops and then adding together like you do in minimization, in the partition function you add together all the loops and then multiply them all together to get your probability.
So what do we get at the end? We get on the left here another prediction, and then on the right here is our scoring. So if you actually went through and compared the predicted values that we have here with the color over here, which represents the probability of any particular one, then it turns out we're getting relatively decent results. Great. So now we have an idea. We need to improve somehow, and there's really two things you can improve now. You can improve the speed, or you can improve the accuracy. If we're going to improve the speed of our algorithm, it turns out we can use a slightly different approach for the dynamic programming and turn our n to the fourth algorithm into an n cubed, which is going to greatly speed it up, and that's one of the things we're looking at.
Or we could work on the accuracy of the program before there's some biological nuances that we haven't quite captured yet in the algorithm, in which a free base next to a paired base actually adds to the energy, and we completely ignore that for now. And we could try and add that in and get a slightly more accurate prediction.
So that's the things that we've been working on over the past semester or two.